pratio, and I have got instead of her because and Dana and Stefania wanted to come to this conference, but there is always lack of funds, you can understand it, but I hope that some other time they will come to have some talk here. This is first the front page of her master thesis, and you can see the title is Test and Meditation Theories by Sagittarius A*, and like Duško said for Stefania, I will not repeat, just to say that she also came here using Erasmus Plus mobility program. I don't know if he said that it was for a period of 3 months, and it was in this year, and main subject field is of course physical sciences. Outline of the talk. It is these results are in fact one part of this thesis, and object and goal would be to present scalar tensor gravity application to stellar dynamics of galactic center. Motivation would be the role of scalar tensor gravity as well as the other modifications of standardized gravity is to explain some observed phenomena without dark matter and dark energy. And we consider possible signatures for scalar tensor theory within the galactic central parsec not tested at these scales yet. We try to explain the observed deviations from Keplerian orbit of S2 star in the frame of this gravity, then we give conclusions and at the end some references which are connected with method used in this thesis. Modified gravity and rotation curves of spiral galaxies. Here you can see that Mont and from here figure you can see that Mont, and from here, from this figure that R and gravity can explain their rotation curves. These are observed rotation curves. And the dark matter is something which is not so good explained this. Extended theories of gravity are physical theories that attempt to describe the phenomena of gravitation in competition to Einstein's theory of general relativity, but preserving the undoubtedly positive results of Einstein's theory. Instead of introducing dark matter, which would be a hypothetical type of matter which does not emit electromagnetic nor interact with ordinary matter, some theories which modify the laws of gravity could explain in a very natural fashion several astrophysical and cosmological observations. And it is aimed to address conceptual and experimental problems recently emerged in astrophysics, cosmology, and high-energy physics, such as rotational velocity curves of spiral galaxies, their baryonic-Tully-Fisher relation, and fundamental planar elliptical galaxies, and some of the alternatives to general relativity. You can see it here. You heard in the previous talk about this scalar tensor modified gravity. I will not repeat this, just to say that for this lecture you have to pay attention on this potential and how it depends on R. Which would be parameters of scalar tensor theory. Scalar tensor theory of gravity contains 2 arbitrary functions of the scalar field, and the specific form of these functions is determined by these parameters, m, c, and lambda. And in order to constrain these parameters observationally, we derive the modified gravitational potential of the central object in the deep field limit to simulate orbits of S2 star, and then we compared our results with the set of S2 star observations obtained by very large telescope. And method which we use, first we choose method. I'm talking about parameters of these gravity, and we want to constrain them. Method for this we choose some values for phi 0, m, and n, with the following conditions: that phi 0 has to be positive real number close to 1, and m and n are integer numbers which have to satisfy this condition. And we vary parameters c and lambda over some intervals, and then search for those solutions which for the simulated orbit in scalar tensor gravity give at least the same or better fit than the Keplerian orbits. And then we repeat this procedure for different combinations of n and n. Here we used these values. We calculated and we obtained calculation for n goes from 1 to 10, and for n goes from 1 to 10, we calculated all these combinations, of course, except this one. And we could try to obtain results for some other combinations of m and n, but you will see later from the figures that it is not so much difference. So it is enough to just to, for now, for this master thesis, to try with these intervals. And what would be this table? It is only one part of the table, of course. This would be minimum chi square obtained for m and n values, but I'm talking here about intervals for c and lambda, and you here can see some certain numbers. Well, for some combination of m and n, we calculate minimum chi square, and values of c and lambda parameters which correspond to this minimum chi square are written in this table. We found for each combination c and lambda which correspond to minimum chi square, and of course it is a whole interval while we are looking for this condition to be better fit than the Keplerian orbit. And so with the parameter space determined in this way, we calculate the simulated orbits and then compare them with the observations. In that way, our results enable us to test scalar tensor theory at galactic scales. And here we have some example. We choose phi 0 to be 1, n 1 and 3, and this would be chi square minimum, and the parameters of the best fit are this c and this lambda. Minimum means that it corresponds to chi square. Of course, it is not minimum value, because when you try to find these values, they are somewhere here, and you can see that they are limited by this red line. It is this line, 1.55. It means minimum chi square, and you can see that we have values until this, and this is just minimum values are limited between these red lines. And here it is presented the map of the reduced chi square over the parameter space c and lambda of scalar tensor gravity in case of these observations of S2 star, and few contours are presented for specific values of reduced chi square given in figures legend here. Then I can show you some other combinations for n and n. I just choose some of them. Then this is for 1 and 4. You can notice that c and lambda parameters are correlated in some way. But how we change m and n? It can be noticed that sometimes quadrants are changed. And this is example for n and n, 2 and 2. And we give one example of S2 star orbit, showing that the gravity we used can provide better fit than the Newtonian gravity. Anna and Stefania divided their parameters. One of two of them draw figures for some values of C and lambda and n, and another one some other values, just at the end they can compare. And Alma choose like to represent her comparison. M to be 1 and 3, these are C and lambda which correspond to minimum T square, and scalar tensor predicts much bigger orbital precession than general relativity. It can be well seen from this zoomed part of the figure. And we can conclude that we derived a particular theory among the class of scalar tensor theories of gravity, and then tested it by studying the dynamics of S2 star around supermassive black hole at galactic center. And we also discussed the Newtonian limit of this class of scalar tensor theories of gravity as well as its parameters. We constrained the parameters of scalar tensor gravitational potential. Aim of Anastasis was to constrain these parameters and to obtain this scalar tensor potential. To constrain these parameters, we compared the observed orbit of S2 star with our simulated orbit, which we obtained theoretically with the derived potential. And here are some references where is used the same method as Anna used for her master thesis. And also in this, there are of course different potential. She's not repeating published papers. She derived another potential, but method is the same. For now, it fits very well for more potentials. Of course, everything can be done even better, and we hope to improve methods. And that would be the case.
Question?
I have two questions. I'm not in the field of understand much about it, but I would like to understand something. So in the modified theory of general theory, one doesn't want to use unknown physics, I mean unknown matter and unknown forces, dark matter and dark energy.
Because in this case we don't need to introduce.
So what is the physics behind the generalization? I mean, the only force is the gravity force, yes, but you suppose some potential, gravitational potential,
which can be added like some additional term to Newtonian term,
yes,
which is smaller, of course, than Newtonian term, but it fixes Newtonian potential. We just add some term and fixes that potential for large, is for larger scales.
Based on some physical considerations, or
maybe I understood what you asked. So let me, for example, these are fundamental theories. What does it mean? It means that they are derived in the same way like Einstein derived general relativity. So practically Hilbert derived. Hilbert postulated some action. In this action, you have Ricci scalar, which he put arbitrarily, without some physical. It was the simplest way to solve. And he then derived, by varying this action, he derived some equations of motion, these field equations. Yeah. And it turned out that it explains a lot of phenomena, but not all of them. Yeah. So the idea is to repeat everything like Einstein and Hilbert did. But why just to assume, let's say, this simplest form of inserted in action? Okay, so it is the way how you form a fundamental gravitation theory. Yeah. You have to, like in mathematics, when you postulate, when you make some axiom, let's say, axiom of parallelism or something like that, you have to start from somewhere. Yes. In fundamental theories of gravity, you start from the action. So it is just a little bit extension of Hilbert's action. And you want to preserve everything that general relativity explains well, and just to extend it to explain another phenomena. So you are searching for such function which can do that. A lot of them cannot do mathematics. Yes, yes.
And the second question is there some hybrid model? I mean, something which includes also dark matter and the modified gravity. I mean, are there some theories like that?
In our results, no. But you mean maybe
or
someone?
Each
For now, I don't know, but it doesn't mean that it. I didn't find for now.
because there should be a lot of dark matter
Maybe.
to explain. I mean,
There are
to
other
explain
theories.
the fact, the observational facts. So many. There is a lot of matter missing. I mean, and does anyone try to, I don't know, make some hybrid model?
Maybe it will be solution. I cannot tell that this what fiber is the best. Of course, it is not. It is just something that we think that it could be, and we will see who obtained the best results. Maybe it would be solution.
Maybe I can add something. It works almost in same way if you add additional matter or this modified theories of gravity. For example, if we have more additional matter, then parameters of this modified gravity will be for sure smaller. Maybe some combination can explain results, but physically we want to we didn't want to use dark matter and dark energy. We don't know what it is, and till now we don't know what is a particle of dark matter and what is the physics behind dark energy. That's why we want to solve this problem in this way, without dark matter and energy. And what is real, true, we don't know. We will see. Maybe something third. I don't know.
I thought because there are some evidences for some dark matter candidates and because of that.
But they are searching for dark matter particles for 30, 40 years, I think, in CERN, so, and they didn't find suitable candidates. So. But taking into account amount of money it was invested in CERN, I'm afraid that
Maybe
they will soon
because
proclaim that they find like Higgs.
It has 4 minutes or so. I will ask one question. Why do you use only two stars?
Because it is good candidate, because it has one of the shortest periods, only about 16 years. It has eccentricity not so big, like, for instance, if it is orbit like this, we have some examples in this eccentricity. This is good. Because of that, because we have observations and short period, we don't have enough observed years for some other star.
Okay.
In the set of S-type stars, S-like stars.
But for example, there is another star, is S102, which has even shorter period.
We haven't observation. We saw it, but we haven't.
On the supplement material on that paper, I think there was no.
But only a few data.
that.
We can't do anything with so small amount.
We didn't have enough data for that.
We haven't done.
We found supplement material on the internet for S2, and for this another, I think we had only few numbers or something.
Okay, so this is the reason, data, because I think it is good idea, for example, for the problem that Zoran if you have two stars, two different orbits, they cannot encounter other black hole in the same time. So you will be able to distinguish potential from other bodies, usually the S star regions. Okay, but data are not displayed.
For now, this is
Okay, so with this we finished this session.
Next session starts at 7, so.
Okay, this is